Hello students, I'm with you today to go through quadratic equations and functions. You'll find that these are some very common equations and functions that come up in many applications, and it's used a lot as you progress in your math courses. So they creep up everywhere, so it's a really good equation and function to know how to solve and how to work with and know some of the properties of them. So we'll start with some basics. We'll do a general overview on quadratic equations and functions, and I get the big picture of how we solve them, how to identify them, and looking at some common properties and features. And then we'll explore more of the properties later on and look into the graphing of quadratic equations in some following segments. So let's start with just the general idea of what a quadratic equation is. So I'm going to take you back to some history of your math, and just what you want to remember is that we have linear equations. And a little recap on a linear equation so we can compare it to quadratic is linear equations, they have this form ax squared, ax plus b equals 0, where the exponent on the variable is a 1. So linear equations have the form of a highest exponent being 1 on your variable. So it's a one variable linear equation with an exponent of 1. And we also have two variable linear equations. So this is a two variable. We're used to seeing the y equals ax plus b, but in most cases, instead of calling this a, we use the value m. So if I change this to m, this might look familiar as being the slope-intercept form for a line. So we have one variable here up to the first power, and we have another variable y up to the first power. So this in itself is a linear equation. Back up here. This is a two variable linear equation. So just remember that these letters are filled with number, this being your y-intercept and this being your slope. So we'll have actual numbers in here. And we fill in our numbers here and here as well, slope and the y-intercept. And we leave these being the variables. So we could graph this in a two-dimensional Cartesian plane. And we graph those points, and linear equations make lines. So now what we're going to do is we're going to go one step above this, and we're going to look at what happens to the algebraic properties when we increase the exponent by 1. So we also want to look at the graph correlation there. So lines were pretty, we've got that mastered, and we're going to move on. And let's take a look at what we mean by a quadratic equation. Quadratic equations. What we're going to start with is the one variable quadratic equations have this form . We have the ax squared plus bx plus c equals 0 format. Now what you notice is the variable is the x. Okay. And a, b, and c are real numbers. So a, b, and c, we're going to deal with real numbers right now. These are real numbers. or I could just use the real number symbol. And the one restriction we have, in order to make it a quadratic equation, we cannot wipe out this term, so a cannot be equal to 0. Okay. So given those conditions, we have our quadratic equations in one variable. So one variable quadratic equation gives you solutions. The solutions we have up to 2 on a real number line. And those will reflect the x values. Okay, so we can solve those, and we can take our real number line and break it up into negatives and positives. And whichever quadratic equation we solve in one variable, we could plot the solutions on a number line. So that's what happens with one variable. So compare this to a linear equation. A linear equation has one solution, up to one solution. One real solution on a number line. Okay, so that's a very important idea there. So you have up to one solution on a number line for linear equations, and here you have up to 2 solutions. Now, it doesn't have to be real, and we'll get to those points a little later. We'll look at some complex solutions as well. Okay. Right now, we just want to make the distinction between these type of equations, and I will give some examples following this. So that's a quadratic equation of one variable. Let me highlight this. Really important to know that, versus a quadratic equation. Okay, I'm going to say a 2 variable quadratic equation. A 2 variable quadratic equation, on the other hand, will have to include that other variable. And typically, they will have the form y equals ax squared plus bx plus c. Okay. Now again, this term is necessary to make it a quadratic equation. This term is not. We sometimes have this, sometimes we don't. This is the x to the first power. So here I have my x variable and I have my y variable. So we have x, y, versus the one variable is just an x. So one dimension, that gives you all the solutions along a single line. And here we're looking at 2 dimensions, which have solutions that you can graph, are ordered pairs or points. So what happens here, again, our conditions are A, B, and C are real numbers. Okay. And A cannot be equal to 0, otherwise we don't have a quadratic equation. We wipe out the x squared term, which is important. And our solutions, we have up to 2 on 2 real solutions. We also have complex solution, but that's to be continued. So I'll put a little note here later. We can have complex solutions. So we have up to 2 real points. Ordered pairs / points on an x, y plane. So at graphical plane. So when you have the two variables, all of a sudden now you're able to graph these quadratic equations. And they make a certain type of graph that is a parabola. And is very much used in a lot of different applications. So the graphs here, unlike previously, the graphs for x, y, here we have our graphs are what we call parabolas. And we will look at these properties in the following segment on quadratics. So the graphs are parabolas. A typical parabola looks like a U-shaped graph that's opening upward, or a downward shaped graph. So very interesting features. And again, like I said, we'll look at a lot of these applications. So one quick one is if we do throw up a ball up in the air, so an application that I always use for quadratic equations in two variables is when we're looking at motion. In this case, we're looking at like projectile motion. So projectile would be like throwing a ball up in the air, firing a pellet, firing a dart gun and watching it fall. So gravity, when you throw things up, gravity pushes things down and it follows this parabolic curve, which can be identified by this type of equation. So I throw this up, it goes back down, and it arcs. Okay, very important. Now, a next detail we want to add in here is the fact that we have quadratic functions. And you've been learning about functions in previous classes. So what we want to do is further identify quadratic equations that are functions. So let's go ahead and add a little bit here. So quadratic functions here we have, there are two variable quadratic equations that will have no repeated x values. So every x is paired with a unique y. So what we have in that case is we can't have repeated x values. No repeated x's must pass the vertical line test. So two variable quadratic equations that must, the VLT, which is the vertical line test, which also says no repeated x's. Paired with y. We have to have unique x values. So just a reminder on that definition of a function. This is the informal definition I'm putting on there. So if you need to review that, go back and review. So a typical quadratic function will have the form, instead of using the y, what we do is we use the f of x notation. We say f as a function of x, as a quadratic, we'll have the format ax squared plus bc, plus bx, plus c. And what happens here is any input we put in for x will be paired with a unique output, which would be f of x. So what happens is we go from y to the f of x format. Okay, this is the same thing. These are your inputs, these are your outputs, your independent variable, your dependent variable. So again, every x is paired with a y in this function format. And typically, we have to note that we don't always just use x and f of x. We might use c of x or v of x or v of t if I'm doing velocity as a function of time. We don't always have to use x and y here. You know, we might have t and v or t and s. We could use different symbols, but the important thing is to identify those two variables at work. So let's take a look at some examples and some last notes here. You just want to make sure that you understand that these are very much similar. So let's take a look at some examples of quadratic equations. Number one is, in math, the number one rule would be to identify what you have, what type of function, what type of equation, and then you're able to know the rules. You want to apply the specific rules for that equation or function and identify what the graphs may look like, which is a good technique in a lot of problem solving. So some examples. Of one variable. Let's start with one variable quadratic equations. So some examples of one variable quadratic equations would be like, let's say 2x squared equals 50. Okay. Now here I don't have an x value. I don't have an x to the first value, but it's still considered a quadratic because it has x squared. In quadratic form, I would go ahead and put it in the ax squared plus bx plus c format. So I'd say 2x squared minus 50 equals 0 format. And here I'd say a is equal to 2, b is equal to 0, and c is equal to minus 50. That's a quadratic equation in one variable. So moving on and giving you another example. Let's say we have 4x minus 20 equals 7x squared. Okay. We see that we only have one variable there. In quadratic form, we would write this as and I could choose either side, 7x squared minus 4x plus 20 equals 0, where my a would equal 7 in this case, b equals minus 4, and c equals 20. So let's set this up a little bit. Let's take a look at what typical two-variable quadratic equations are when we actually have values for the a, b, and c. So here we have two-variable quadratic equations. And two-variable quadratic equations will look like, let's say, for instance, y equals 2x squared in this case, and I'm going to use the same thing. Let's say minus 50. So if we want to add a variable into this statement, we would put in a y, or we'd pair the x up with a dependent variable. So here I have ordered pairs that map out into where all the ordered pairs are points that map out into some sort of parabola, some sort of graph that we can picture and put together. So here we have every x is paired with a y, and in this case again the same thing holds. Here in quadratic form, or I should say in general form is another term for it. In quadratic form, this would be y equals, in quadratic form it's the same thing, right? It would be exactly the same. So I'm going to make a little note here. General or standard form. And we'll get to more of that. in quadratic form. We have that, but we could go ahead and identify what our A, B's, and C's are. So A equals 2, B equals 0 again, and C equals minus 50. The next thing we want to do is take a look at an example that is maybe different. So here I have another quadratic equation in two variables. So y equals 4x squared minus 7x plus 2. And this is what it's going to be when I put it in quadratic form, or what we call standard form. Okay, just be aware that these are interchangeable terms. Standard form is mostly the universal language that they use in textbooks and in the definitions. So in this case, A is equal to 4, B equals minus 7, and C equals 2. Okay, now a function is very much going to be the same sort of format, except instead of y, we're going to replace that with f of x if we know that it is a function and passes the vertical line test. So a quadratic function example, let's take a look at some. Quadratic function examples. Okay, so quadratic function examples. Number 1, we would have instead of y, we'd have f of x equals 2x squared minus 50. And the only difference now is we're calling this a function. It means something. It means it's going to pass the vertical line test. But all things are exactly the same as far as the identification of the coefficients, the A, B, and C. So here, A equals 2, B equals 0, and C equals minus 50 again. Okay. Another example of a quadratic function. Well, here's another one. F of x equals, let's say, 4x squared minus, I'm going to add a little bit here. Let's say I had 4x minus 1 squared plus 2. Here we have a quadratic function as well. It's not as evident as the other ones, but I know that when I multiply this out, I will get an x squared term. So if I multiply this out and put this in what we call standard form, quadratic form, what's going to happen is this becomes 4 times x minus 1 times x minus 1 plus 2. And this is the same thing as saying 4 x squared minus 1x minus 2x plus 1 plus 2. And moving on over here, we get f of x is going to be 4x squared minus 8x, and then I have plus 4 plus 2, which is plus 6. Okay, all that. These are equivalent functions, but this is in the quadratic form, the general form, the standard form that we use. So standard form probably is the best language. I should have started out with that, but that's a little bit of a terminology issue. Okay, sometimes I interchange those words a lot when I'm doing quadratics, but they mean the same thing. Next step here, what I want to look at, I know there's many other examples, okay, that we're going to come across, and I'll put one more up. Let's take a look at something that's not an f of x, but I'm going to use something that I frequently apply in physics, a velocity versus time function. Let's say I have velocity versus time is like 2t squared plus 4t minus 10. So this is another quadratic function. So here we have a quadratic function in two variables. In two variables. The only difference is the ordered pairs, the points that we have that make up this function will be in a t. Time is usually what we use. We say velocity as a function of time, where time is measured in seconds, and we can figure out how many meters per second an object is going. We have time as our independent variable, and instead of a y, we'll use our velocity as a function of time value. So whatever the input produces, so whatever input we put in here would go here for our independent variable, and the output that's produced will be the velocity value, and that would be right here. So there's another example of a quadratic function. And then other ones that come up, you might have f of x equals 2, 1 minus x squared plus 2x. So there might be a lot of work involved, and obviously this is not in your standard form. So this you work out and get in standard form. Now there's another format that we typically have quadratic functions in, and that is your vertex form. This is in what we call a vertex form. And this sort of format is applicable when we deal with graphing. So let me point that out. We'll say this other format, we'll introduce this other format before we move on to some other operations. So, quadratic functions. And we'll see this a little bit more later when we do graphing. We'll see more of a distinction here. The two main formats. So we've already looked at your standard form, which is going to have a lot of uses, especially when we're applying something called the quadratic formula. So our standard form is the f of x equals ax squared plus bx plus c format. Again, remember, we use y a lot of times. That's your standard form. And then we have also the vertex form, which is very useful for graphing. And the vertex form for a quadratic function is when you have it in the f of x equals a x minus h squared, h being some number, plus k, where, again, a is not equal to 0, and h comma k, this value makes an ordered pair. So h is the value that's part of your independent variable in your ordered pair, and k is your value. And that's going to give you something called the vertex, where hk is the vertex. That's going to be something we're going to look at. That's the opening point of the parabola. That's what your vertex will look like. And we'll see that these open up or down. And this is what the vertex is, this point. You highlight it. Okay, that's given by hk. So this format is really nice if you're graphing because you can pick out what the vertex is. It's also really nice when you're trying to solve an equation given that format. You could use your square root property there. And one more thought here, just a reminder that a is not equal to 0 here as well. Okay, so that's a lot of stuff in your overview. And the last thing I want to be able to just highlight here, some of the things you want to do with quadratics, some main properties to explore or add to your knowledge template of math would be domains. What's different about the domains of quadratics, the ranges, some of the other features that we have are minimum and maximum values. So we'll look at that as well, in addition to what the vertex is, something called the axis of symmetry. We'll see there's some symmetrical features of the graph that a quadratic function makes that we could use to assist us in graphing and apply. So we want to understand what that is. We want to take a look at our intercepts, x and y intercepts. It's another property we want to explore. And we want to, in addition, look at, make sure I have all these, minimum and maximum values. And we want to look at what the graphs look like, which are a special kind of graph called a parabola. Okay? So there's a lot of features. There's a lot more features to what quadratic equations and functions make than just a line. A line is just a line. So there's not much you could do with a line. Well, there is, but it's as far as graphing goes, you only need 2 points to make a line. You need a little bit more to do in order to plot a quadratic. Now let's go ahead and talk about the main ways of solving equations. So I'm going to leave off there, and then we're going to do a series of lectures on how to solve how to solve quadratics using all these techniques. So solving quadratic equations, which, if it's a function, you can make it an equation by setting when the variable is equal to a value. So this applies to functions as well. So solving quadratic equations, there's 4 main ways. Now I'll go in increasing order of difficulty. So the easiest way to solve, if you can, is by factoring. And I'll say via factoring, if it's possible. So previously, if you couldn't factor something, you'd say non-factorable, or you couldn't solve it, and we'd be stuck. But we'll find there's other techniques we could apply. So the second one is via the square root property, which is a really nice feature. If your quadratic function or equation is set up in a certain way, you could just take the square root of both sides and solve for x. And 3, what we want to look at is via factoring square root property, completing the square. This is a little bit of a mess. It has a lot more detail. But the technique can be useful if you want to put a quadratic in vertex form and solve for the vertex. And 4 is via the quadratic formula. One of those formulas that's a must memorize in math. So the quadratic formula is very useful comes up a lot. I've come across very ugly quadratic equations where I couldn't do anything but use the quadratic formula, and that's how I got my solution. So what I usually do is I say, okay, if I can't factor it, what I do, if can't factor, I would go right to the quadratic formula and use that. Unless the setup allows me to do it by the square root property. I typically do not use this third technique unless I really have to. So these all have their special ways of solving quadratics, and again, sometimes you might get a really messy problem where the only thing you could do is apply the quadratic formula. So what we're going to look at is all these different techniques, and I think I'm going to actually add solving by factoring first, and then we'll do a follow-up on square root property and completing the square. So how would we solve a quadratic by factoring? So I will go into one technique. A little bit more time left, so I'll start with that. So solving by factoring. This is a little bit of a review, so I don't want to have that added into the next series of lectures. So one thing is, if we could factor it, we could factor it, and it's nice and easy to do. We could always check our answers with the quadratic formula when we know that. So there's more than one approach you can use for any type of equation. Sometimes you're only stuck doing one. So let me give you an example of solving by factoring. These should be familiar. So this is a review. Let's say I just get the directions solved, and I'm given a problem like set x squared minus 7x, and then what do I have? Plus 6 equals 0. So this should look familiar. The idea is, here we identify a quadratic equation. It's in the ax squared plus bx plus c format. And what I want to do is I want to get this whole side factored, and this side set equal to 0. So here my factors will be, it's my regular factoring technique, x minus 6, x minus 1, so that minus 6 times minus 1 add up to plus 6, and my middle terms minus 6x and minus 1x add up to minus 7x. So this whole thing is equal to 0. And the idea with the factoring, the zero factor principle, is you set each factor to 0, factor with an x in it. All right, so x minus 6 equals 0, x minus 1 equals 0, and we get x equals 6, and x equals 1. So we got two solutions. And if you remember in the beginning, we said you could have up to 2 solutions for quadratic. You always have up to as many solutions as your highest exponent. So this is my claim, and before I claim that, I could do a real quick check. Whenever you solve something, you should always be able to check it. So let's see, 6 squared minus 7 times 6 plus 6, does that equal 0? Well, 36 minus 42 plus 6 equals 0, it indeed does. So my solutions must be correct, they work. Okay, that's a typical solving by factoring problem. And of course, you could have many other types of problems. Let's say we had we had 12 minus 2. 1 second. Oh, this is a good one. 12 minus 2x squared, and then we have equal to 5x. Let's try to attempt solving this quadratic equation. So if you look at it, we know it's quadratic. What we want to try to do if we're going to attempt to solve by factoring, maybe we don't want to bother with the quadratic formula, etc., or any of the other techniques, we are going to go ahead and bring everything on one side and set the other side to 0. Now what I'm going to do is either factor out my -1 or divide by that -1 because I want to make sure this is positive when I'm factoring. So just a little review on that. That changes the sign of all my terms on the inside. And what I could do is multiply both sides by a -1. It's just a -1, so let me get rid of it. Whatever I do to one side, I have to do the other. I have to keep the balance. So what we have now is 2x squared and plus 5x minus 12 equals 0. That makes it a lot easier. Next step. Okay, I have a non-1 coefficient here. So it makes things a little trickier to do, but I want to come up with combos. I like to do trial and error. Combos that make up this first combination, 2x and x. So 2x times 1x is 2x squared. And then I got to come up with a factoring combo of minus 12 that will add up to the positive on the inside. So I have, if I look at 12, I think of the factors 1, 12, 2, 6, 3, 4. So how do I place a 3, 4, a 2, 6, a 1, 12 here so that I make the right combination? I can kind of see where it's going. I can see that if I put a plus 4 here and a minus 3 here, that my inner terms minus 3x plus my outer terms plus 8x equal a positive 5x, and I have the magic combo. That works. So now what I would do is now what I'm going to do is set each factor to 0. So I have 2x minus 3 equals 0, and then x plus 4 equals 0, and this ends up being 2x equals 3, divide by 2, divide by 2, and this ends up being x equals minus 4. So I have x equals 3 halves and minus 4. Those are my final solutions. And what you could do, again, you should do, especially on a test, is insert these in place of x. If I claim these are solution, I should be able to put the -4 here, square it, minus the 2, minus 4 squared, add the 12, and that should equal 5 times the -4. And the same with the 3 halves. Okay, one last one that will be a preview on a really good technique to do in the next section. So here, let's go ahead and solve something that's like, let me say I have I'll say 2x squared equals 50. If we're going to solve this by factoring, what I would typically do is bring everything over again, everything on one side, 0 on the other, and I would divide out by 2. So I could just go ahead and straight out divide, or I could factor out the 2. Well, let me just go ahead and show you. Divide by 2, divide by 2. And now my next step would be x squared minus 25 equals 0. Then we would apply the factoring technique of difference of squares, which would be x minus 5, x plus 5 equals 0. We get x equals 5 and x equals -5 as my solutions out of that. And that would be your final answer. Now, an alternative way of doing this, which we're going to see, is, well, you could kind of sort of see what the answer is. Now, the whole idea is, what does this x need to be as far as a number in order that when you square and multiply by 2, you get the value 50. So you can see this has to be a -5 or a +5. It's the only thing that when you square it would make this combination. So a quick way of doing it is applying something called the square root property, which is going to be the next property to explore. But just a little preview, if you want to work ahead, is This next step is 2x squared equals 50. And we'll say alternatively, and you might have spotted this if you were being a little clever about it. You could see that if I just go ahead and divide both sides by 2, I would get x squared equals 25. And hey, why don't I just take the square root of both sides? Which you can do. So what I can do now is I take the square root of x squared, and when I take the square root of 25, when I take the square root of 25, I have to realize that there's 2 possible roots there. I have to use a plus and minus sign out in front, and so I have 2 possible roots here, and x is equal to a positive or a negative 5. Or in other words, x equals negative 5, positive 5. I get the same answer. And that's the core of the square root property that we're going to come to next in completing the square. So to start, look at these quadrats, try to factor them, and see if you could try to identify any that have the square root property, because it's a very quick method to use. All right, that's it for algebra for now, and we'll continue with more lectures coming up. Thank you.